Welcome to Miss Smith's Math Tutorials. I'm Miss Smith. In this video, we're going to be talking about exponential growth and decay again, but now we're going to be really using the formula as it's meant to be used, which is in real life examples, so word problems. So I think I've got five word problems that we're going to walk through. By the end of it, you'll totally get the hang of it. They're a little weird at first, but it'll make more sense the more you do them. Okay? So, starting with this first one, a population of 3,000 people doubles in size every 10 years. Determine the population after 50 years. So, this is an exponential word problem, so we're going to be using our formula, y equals a times b to the power of x. So in my last video, you'll recall we said A is always our starting point, B is our rate of change, and X is our time. So we need to figure out each of those three things, plug them into this formula, and solve to figure out our answer. So let's start off with, I've got my y equals. A is my starting point. This is usually pretty clear in every problem. So it says a population of 3,000 people. That's my starting point. So it's 3,000 is my A value. That's my starting point. All right, my B value. So it's 3,000 times my B. So that's going to be my rate of change. So I'll notice that this says a population of 3,000 people doubles in size. So we got to use a little bit of kind of outside the box thinking here. If something doubles in size, that means that it is being multiplied by 2. Okay, in the same way, if it said it triples, that'd be times 3. If it quadruples, that'd be times 4, and so forth. Okay, now for my x value, so it says, we got to be real careful here. It's easy to make a mistake. It says a population of 3,000 people doubles in size every 10 years. So determine the population after 50 years. You've got to think of it. I know it's tempting to put, okay, 50. It's 50, right? Because it's 50 years. No. It doubles every 10 years. So we've got to think about one doubling period would be 10 years. Okay, so 2 doubling periods would be 20 years. All right, 3 doubling periods would be 30 years. So using that same train of thought, 5 doubling periods would be 50 years. Okay, so what is our x? It's the number of doubling periods, so it would be 5. 5 doubling periods. So that's kind of how I like to break it down, and that's what I'll use whenever it's needed. It's not needed on every single problem, but definitely when it talks about things that double or triple or whatever, increase a certain amount or decrease a certain amount every so many years, and it gives you a number other than 1. That's when doing this is very helpful, just to kind of lay it out. Okay, so now that I've filled in my equation, I've got my A, my B, and my x value, I just put this into the calculator, and it does all the work for me. So I'm going to bring out my calculator, cut it on, and I'm going to type this in. So 3,000 times 2 to the power of 5. It gives me y equals 96,000. Okay, so what does this mean? Because it's important not to just have an answer, but to really state what that answer means. So the answer would be, we're determining the population, so after 50 years, the population would be 96,000 people. Okay? Let's look at some more examples. In 1990, a small town had a population of 15,000 people. Since 1990, the town has increased 3% per year. What was the population in 2005? Okay, so this is definitely an exponential either growth or decay. In this case, we want to look for, and I did not do this on the first problem, which was my bad. The first problem was a growth problem. It did double in size, so I should have noted that. So if that's helpful to you, make sure that you notice that that is a growth problem. I'll be more careful of noting that on the next ones. So I'm going to be using my exponential formula, and I need to plug in what is my a, b, and what is my x. So remember we said A is always our starting point. So what is our starting point in this case? 15,000, right? Because we're starting this, survey of sorts in 1990, and there were 15,000 people in there at that point. Okay, now we need to work on our B value. So our B is our rate of change. So it's increased 3%. This gets a little tricky. Okay, we cannot write in for B 3%. Okay, we can't do that. Anytime it gives it to you in a percent form, there is a two-step process we have to go through. We have to do both of the two steps or it will lead to a wrong answer. So make sure you are doing your first step. Your first step is turn that percent into a decimal. Okay, so 3% as a decimal would be, now there's a couple ways you could go about this. You could either do 3 divided by 100. That's one way. You could remember that we move our decimal place over to the left. That's another way. However you like to do it, our answer would be 0.03. That's our first step. Okay, our second step to get our B value when given a percent is to ask ourselves, are we increasing or are we decreasing? Is this growth or is it decay? Okay, so we had the population of 15,000. It has increased, as a key word, increased 3%. So when it increases, you do 1 plus that decimal value, 0.03. Okay? If it was decreasing, we'd do 1 minus 0.03. But don't let that confuse you. We'll get to an example where we see that. Okay, but because we're increasing, this is growth, we add the 1. Okay, so our answer would be 1.03. That is our B value. Okay, you've got to go through not only the first step, but the second step as well. Now we have our B value. So 1.03. Okay, and to the power of x. So what is our time? Well, in this case, we're talking about years. And it says, so we're going from 2005, but we're going all the way back to 1990. So we need to know what is the difference in those years. So you could literally do 2005 minus 1990. Okay, I'm going to do it on my calculator to save some time. 2005 minus 1990, which would be 15. So that's a 15-year difference. Okay, so now that I've got this in, I'm going to put it directly into my calculator. 15,000 times 1.03 to the power of 15. Okay, so we got to be kind of careful here. You'll notice I get a long decimal. I cannot have a decimal of a person. Either it's a whole person or it's not, no person. Okay, so we round to the nearest whole number when we're talking about people. So in this case, it'll be 23,300, and we'll round that up to 70 because of that 0.5. So it would be 23,370. Okay, so what does that mean? We need to take that next step and really not only just list the answer, but what does that answer mean? So in 2005, the population was 23,370 people. Okay? Here's another example. The total gallons of juice each person consumes yearly has decreased 4.1% each year. In 1981, each person drank 16.5 gallons of juice on average. What was the approximate amount consumed per person in 2010? So I have no idea if this is true or not. Probably not, because I made it up. So, but let's pretend that it's true and go ahead and figure out what the amount of juice consumed in this year was. Okay, so we're definitely talking about an exponential problem. So I'm going to use my exponential equation. Y equals A times B to the power of X. And I just need to fill in each of those parts. So what is A? A is my starting point. So we're going to go in 1981. What was the starting amount? So it was 16.5. Okay. So what is B? B is our rate of change. So I notice that this is a percent. So when we have a percent, I cannot just throw in here 4.1%. I've got to do a two-step situation. Okay. Step number 1, turn that percent into a decimal. So whatever your method is, moving the decimal over 2 places, dividing by 100, whatever you like, 4.1% as a decimal would be 0.041. Okay? Can't stop there. That's not our B yet. We got to do part 2. So part 2 says that I need to take that and I need to decide. Am I decreasing or am I increasing? Is this growth or is it decay? You've got to look at your keywords in the problem. So I see that says that this is decreasing. The amount of juice people are drinking is going down. So in that case, I will do 1 minus that decimal. Okay, remember in the last example, we said if we're increasing, it's a plus. We're decreasing, it's a minus. Okay, so 1, I'm going to do that on my calculator. 1 minus 0.041 would be 0.959. Okay, there is my B value. I went through both steps, so I know I have it. 0.959. Okay, I still need my X value. We're talking about years again, just like we were on the last problem. So I got to figure out what is the difference in the years. So we're going from 2010 all the way back to 1981. Okay, so I want to find out my difference here. So my X value is a difference of 29 years. So now that I've got my formula, I've got each part filled in, I can just put it straight into my calculator. So 16.5 times 0.959 to the power of 29. Okay. Now, I definitely want to round that decimal. I do not want to list that whole thing in my answer. And it says approximate. We're talking about gallons. So you can absolutely have, a half a gallon or a third of a gallon or, a decimal of a gallon. We can't do that with people, but we can with things like gallons. So it didn't specify in the question what to round this to. You could do 4.9 or you could round up to 5. Either one would be correct. I'll just stick with y equals 4.9. Okay, so I want to write out what does that mean. So in 2010, 4.9 gallons of juice on average. So that's per person. Here we go, next example. You buy a car for $35,000. Its value depreciates 10% every 6 months. How much is the car worth in 7 years? Okay, so I know we're talking about our exponential equation, so I'm going to be filling in y equals a times b to the power of x. Remember, a is our starting point. So in this case, our starting point, how much is the car worth when you buy it? It's worth $35,000. So that's our starting point, our starting value. And then we've got to fill in our b, and it gives us another percentage. So you know what that means. I've got to do a two-step. Okay, first thing I got to do is turn that decimal, or turn that percent into a decimal. Okay, you can use your decimal trick, you can divide by 100, but however you do it, you're gonna get, you're gonna get 0.1 or 0.10, doesn't matter. Okay, now I've got to take that and do step 2. I've got to ask myself, is this increasing or decreasing? So here it doesn't actually use the word, but it does say, it doesn't use the word decreasing, but it does say depreciates. That word means it's going down, it depreciates. So that's a word I would definitely be able to recognize. Depreciates means decreases. So because we're decreasing, I'm going to do 1 minus that decimal, 0.10. Okay? If it was increasing, we'd do plus, but it's not. So our answer here would be 0.90 or just 0.9. That is our B value, okay? Got to do both steps. All right, now our time here, we've got to be very careful. It's easy to make a mistake here. It says the value depreciates every 6 months. How much is the car worth in 7 years? So I know it's so tempting to just skip, and I almost did just a second ago, skip and write 7. But that's not accurate, okay? Because it's 10% every 6 months, not every year. So we've got to think about this. Like, 1 year would be how many cycles, how many periods of this decrease of 10%? Well, it would be 2, right? Because there's 6 months in every year. So that would be 2 periods, we'll call it, okay, of decreasing 10%. So in that case, 2 years would be how many periods? Well, that would be 4 periods. All right. What if I said 4 years? How many 6 months periods would that be? Well, that would be 8 periods. Okay, so let's think about 7. Keeping this pattern going, 7 years would be how many periods? Well, it'd be 14. I'm just kind of multiplying because I know it's 2 periods per 1 year. And if you struggle with making that jump, going from 2 to 4 and from 4 to 7, then don't make the jump. Lay it out. Do 1 year would be this many. 2 year would be this many. 3 year would be this many. Lay it out all the way to 7 if that's what you need to do. Okay? But either way, it's 14 periods of the 10% increase. So really important to note that. All right, now that I've got my formula laid out, I'm just going to put it right in the calculator. 35,000 times 0.90 to the power of 14. Okay, so my y is, and we're talking about money, so you could either round to the nearest dollar or round to the nearest cents. I'll do cents just because we'll be exact. Okay, so it's $8,006.88. Okay, so let's sorry, that's gross. Okay, so let's talk about what that answer means. So after 7 years, the car is worth really only $8,006.88. Okay, think about that. You bought the car, you spent $35,000 on it. After 7 years, it's only worth approximately $8,000. So kind of the tough thing about owning cars. All right, we've got our last word problem here. Last one. All right, so Barbara puts $100 into a bank savings account. The account accrues a 9% interest rate compounded annually. How much money is in the account after 12 years? Okay, so anytime we're talking about money and interest rates and things like that, you're definitely going to be using your exponential growth / decay formula. Okay, so we just need to fill in each part of this. A will always be my starting point. So how much money did she put in the bank account from the get-go? She put in $100. So that's our starting point. Now I need my B value. Again, they love giving us those percents. So we've got to get used to doing our two-step to turn that percent into an actual B value that we can use. All right, first step, turn that percent into a decimal. So whatever method you want to use, you should get 0.09. Okay, step 2, take that and decide, are we increasing or are we decreasing? Now I know this 9th graders are not really used to learning about interest rates yet. And, it kind of comes when you get older. So pretty much any time you're talking about, putting money in a savings account and interest rates, your money is increasing, okay? And that word accrues, that means it gains, okay? So over time it will accrue, it will gain this amount of interest compounded annually. That's a phrase you're going to see a lot, interest rate compounded annually. All that means is that you would get this percent of your money back in interest, gained in interest once a year. So throughout the year, you should get 9% of your money given to you as kind of a bonus for keeping your money with that particular bank. Okay, so just kind of some side information there. But the fact that it's accruing means it is going up. So we would do 1 plus, because we're increasing that decimal, 0.09. So that's going to give us 1.09. There's our B value. That's what I can use. So 1.09. All right, now my X, my time, this one I really like. It's super easy. It's compounded annually, so it's once a year, and we want to know how much is in there after 12 years. So 12 would be our X. I like those when it's just nice and simple. We don't have to worry about doubling periods or anything like that. Okay, so now that I've got my formula all filled out, I'm going to put it in the calculator. 100 times 1.09 to the power of 12. All right, now we're talking about money again, so you can either round to the nearest dollar or to the nearest cents. I'm going to do cents in this case. So Y equals 281. We'll do 27. Okay, so what does this mean? It means that after 12 years, Barbara has $281.27 in her account. I guess it's pretty good. After 12 years, she started with this. Now it's grown to that. When you put a lot more money on there, it'll get even bigger. So always a good thing to save money. All right. This has been Miss Smith's Math Tutorials.